Hello, everyone, and welcome back to your series of probability and statistics. Last time, remember we had a problem at the end that I wanted to plot using my TI-84, and for some reason it didn't work. And sure enough, after the session, it worked just fine. And basically, I want to show you how to do it. Just to remind you, it was um, finding the probability that our X bar is greater than 107 less than 112. Mu was 110 and sigma was 30 and n, the sample size, was square root of 40. Right? I think that was it. And we got this probability to be roughly 0.4, if I remember correctly. And I told you the way you do it, you go second this distribution, but then you go to draw and select shade normal distribution. Shade norm, it asks you for the lower limit 107, comma, the upper limit 112, comma, the mean 110, comma, and the standard deviation, if you remember, the standard deviation of the mean, not the standard deviation of the population, is 30 divided by the square root of n. So 30 over the square root of 40. And you get 107 to 112, and they show you the area and also the area as a magnitude, 0.39981, and they shade the area under the curve between 107 and 112. Anyway, it's not a big deal, but for some reason it wasn't working yesterday. Okay, today's topic is about the confidence interval, confidence interval, for short CI, of mu, the mean of a population. So before we start that, we are going to discuss the difference between a population and a sample, okay? So what is a population? Like, do you understand what a population is? A population is a whole, word. It's most of the time infinite. So sometimes it's finite, but with all, like when you say normal distribution, that's an infinite distribution. The exponential distribution is an infinite distribution. Okay? And a sample. This one is infinite, at least the ones we will be using. And this is, of course, the sample is finite. The population contains stuff that we call parameters, like mu, like sigma, like lambda for the exponential. These are called parameters. But the sample has its own mean and standard deviation. We call them statistics. Yeah, like the name of the subject. It's probability and statistics. These parameters can be calculated. They are estimated. So you give me estimates of that. But these can easily be calculated. So what are the parameters? We said they are the mean, the standard deviation, the median, the variance. And the statistics are also the mean, what? So how do we differentiate between them? Usually here we use Greek letters. So we refer to the mean with the letter M or mu. For sigma, we use sigma or S, the standard deviation, or the variance, sigma square, and so on and so forth. Here, we use just Latin. So the mu, we call it X bar. The standard deviation is S. The variance is S square, and so on and so forth. You may see in the future, especially when we work in statistics, that the X bar, the S and the S square are written like that. Mu hat, an estimate of mu. So please don't get confused. You say, oh, that's Greek, so that's the population. No, that's not the population mean. That's the statistics or the sample mean. But we are just reminding you that we are finding an estimate of mu, an estimate of sigma, or an estimate of sigma square, and so on and so forth. These are the same, okay, synonyms. So we'll be using the sample statistics to estimate the population parameters because they cannot be measured. But if they are estimates, you want your estimate to be good, right? So suppose in this problem, I calculated X bar, I don't know mu. In fact, in real life, you never know mu. Remember when I told you if you are producing, say, steel bars and you want to know exactly mu of the tensile strength of your production, you have to break all of them. And notice while you are breaking them, you are producing more. So you stop production and you break all your thing and you will be out of business right before you start even, right? So nobody does that. So mu is unknown and unknowable, not just unknown, unknowable. You can't. Same thing with sigma and same thing with all the parameters. They are not known for sure. So you have a problem and your boss, because you have a big project done for a client, you want to improve the quality of the production, and somehow they have a physical unit that you are measuring, and you get 109.4. So your boss, you say, okay, did you estimated the population mean? You said, well, yeah, 109.4. So he said, how confident are you that this is their mean? Because that's great news. I'm going to call the guy. You say, oh, that's a continuous distribution. So the probability that mu is exactly 109.4 is zero. Should I tell him zero or I will be fired? Well, sir, I'm not that confident it is. He said, no, I don't like that. I want you to tell me how confident are you? Give me a percentage. I'm 0% confident. You must be kidding, right? You've been working on this project for like 3 weeks and you come to tell me that you give me a number and you say you're not confident. You're not confident at all that it is correct. No, no, no. I didn't say I'm not confident it is correct, but I didn't say it's not precise. Okay, so give me a better thing. Give me can you be 100% confident? I'm sorry, sir. I know this cannot be negative. So in order to be 100% theoretically speaking, the mean is between 0 and infinity. Oh, so you're making fun of me. Go get your pink, I'm gonna give you like you are fired, so to speak, right? The pink slip, you know that? So say, sir, I cannot be 100% confident, but I can give you any confidence below that. So are you telling me you can tell me you are 99% confident it's between two values? Yeah, even 99.9, I don't care, but not 100%. So this guy is like, okay, I'm settled for 95%. That's good enough. So yeah, that's great. So give me two numbers that you are 99% confident they capture the true mu, even though you don't know it, but you are 95% confident that it captures mu. Notice I didn't say a 95% confident that mu is inside the limits. I know it's a technicality, but mu is a specific number. It's not a random variable. It's constant, right? So I cannot say the probability that it's inside the range. It's either inside or outside. But there is no, I know it doesn't make perfect sense to you when you hear it the first time, but you can be confident that if I give you two numbers I am confident that these two numbers capture mu between them. So it's like mu is here. 95% of the time, I will give you numbers that include mu, but 5% of the time, maybe 2.5%, I will give you these two numbers, and 2.5% I give you these two numbers. So mu is outside. Okay? Notice I don't know where mu is. So, but this is mathematically sound. I can give you these and tell you there is a 95% chance that the numbers I gave you include mu. Okay, so away from this technicality, what are you really trying to tell me? I'm trying to tell you that here is the normal distribution, but this is the normal distribution of x bar, not of mu. So I'm going to give you two numbers here where this is x bar, but I know that the expected value of x bar, meaning the mean of x bar, is mu. We proved that last time, right? So, but this is x bar, and this is a lower limit, and this is an upper limit. So I can give you the lower limit and the upper limit. How? Easy. We have the, I'm not going to use the x bar because there is infinite x bar and sigma, right? Remember what we did? We went to another axis of z, and we said here is 0, this guy is 1, this guy is -1, and I'm going to give you two numbers. We call that z alpha over 2, and this is -z alpha over 2, meaning this area to the right of the z is alpha over 2, and this is alpha over 2 for a sum of alpha, meaning the area between the two lines is 1 minus alpha. So if alpha is 5%, I give you a 95% confidence interval. If alpha is 1, I give you a 99% confidence interval, and so on and so forth. How do we do it mathematically? I want to find two values, or a value of z alpha over 2 and -z alpha over 2, such that the probability that my z value, notice my z value for the mean, we said z equals x bar minus mu over sigma over root n. The estimate minus the parameter divided by the standard error of the estimate, because the parameter doesn't have error. It's a single value. The mean of x bar is the expected value of x bar, which is mu. Sigma over root n is the standard deviation of x bar, which is the standard error of x bar. Okay, and that's why we said if we increase n, we are decreasing the error, meaning we are getting these two lines closer and closer to each other. Okay? So, I want the probability that my random variable z, which I can write as x bar minus mu over sigma over root n, to be greater than -z alpha over 2, less than z alpha over 2, is 1 minus alpha. So alpha is 5%. This is a 95% confidence interval. You say, but that's not easy. I want just mu to be greater than what, less than what? Okay, so I'm going to multiply the three sides by sigma over root n. The probability at -z alpha over 2 sigma over square root of n is less than x bar minus mu is less than z alpha over 2 sigma over root n to equal 1 minus alpha. Okay, but that's not good enough. I want mu. You say, but this is x bar minus mu, so let's multiply everything by -1. So that becomes z alpha over 2 sigma over root n. You learned in algebra when you did inequalities that if you multiply by -1, you are switching those guys, right? And this becomes mu minus x bar. And this becomes negative Z alpha over 2 times sigma over root n. Usually we write, if you bring this here, so if you write it backwards, funny thing, it becomes the same as the top, right? Because you are going to bring this here and you say it's less than mu minus x bar is less than this guy, z alpha over 2 sigma over root n. So funny, right? It's because this guy is the negative of that. So when you multiply by negative and then you switch, they return to where they are. And finally, you are going to add x bar to each side. So you say the probability that x bar minus z alpha over 2 sigma over root n to be less than mu to be less than x bar plus z alpha over 2 sigma over root n is your 1 minus alpha percent confidence interval. Oops. This is called the 1 minus alpha percent, 100 times 1 minus alpha percent confidence interval of mu. We know that for 95% confidence interval, you want 2.5 to be to the right and 2.5 to be on the left, and roughly z alpha over 2 here to be roughly 196. If you want it 90%, then alpha is 10, meaning alpha over 2 is 0.05. Then z alpha over 2 would be roughly 1645. And you can do 99. So suppose I want to find these numbers. How do I find them? Again, very easy. You can go to distribution and do the normal confidence. Okay? So you want the lower limit. You know, the lower limit here is negative infinity. Remember we said negative 1 EE 99, comma. No, but here if you know the number, let's do the probability. Okay, let's do the cumulative. Yeah, we can do the inverse normal, right? Because I want the area to the left to be 0.025. The mean is 0, the standard deviation is 1. And you get negative 1.9599, which I told you it was 196 and negative 196. Okay? If you wanted 5%, you get that. If you want 1%, second, oops, what did I do? Oh my God, what? Why? I keep pressing second distribution. I want the inverse, where this area is only 0.01, you get 2.33, if I remember, something like that. Yeah, negative 2.33. If you wanted less than that, you can go even to 258. Anyway, but you can easily construct the confidence interval using this method. Okay, we can do it for any problem. So let's say we calculated x bar and it was whatever 19.2. And the standard deviation of that was 2, and your sample size was whatever, 5. Construct a confidence interval for mu. So you say mu is greater than 19.2 minus, if you want, we said 99, I think I said, 99% confidence interval. We knew that I want this, if it's 99, I want this to be 0.005, and you will get roughly z 0.005 is roughly 2.58, if I remember correctly. 0.005, comma 0, comma 1. Yeah, negative 2.575. We usually use negative 2.58 times sigma over root n less than 19.2 plus 258 sigma over root n. Again, it's easy to calculate. You can do it with the calculator. We'll learn that later. I mean, you use the statistics and you go and find that, but this is easy since we are making the numbers. So I can say plus because that's negative to get the lower limit, times 2 over the square root of 5, and I get 1689 or 16.9. Notice the difference is roughly 2.3. So if I add 2.3, I can get the upper because the mu is always exactly in the middle. Or I simply can come here and delete the negative in front of the 258. Just delete that. And you get 21.5. Notice that the average of these two numbers would be the 19.2. 2.3 below, 2.3 above. And that's it. Okay, so that was a short session. I just wanted to introduce that, and then I will give you the bad news. Should I give it to you now or next time? Yeah, I'll give it to you now, just to try to absorb it before next session. Almost invariably, impossible, we know sigma. Sigma is unknown. Say what? So why are you doing all of that? Well, this is consider it as an exercise, so you know how to develop the confidence interval. But do you really believe that I have a process for which I don't know the mu? I don't know mu, the mean, which is easier than the standard deviation, right? You see how we calculate. In fact, in order to calculate the standard deviation, we need to know the mean. So if you don't know the mean, how on earth did you calculate the standard deviation? I told you they are estimated, not calculated. And then I tricked you and I say, okay, so let's divide by sigma or multiply sigma because I know sigma is 30. What? It's impossible to know sigma without knowing mu. Two reasons we use that. First, to introduce the topic as we lay the foundation in probability. And then secondly, because in the old days, it was so tough to calculate uh, the probability without knowing sigma. We couldn't use the z, the normal. Remember, we developed only one normal table. We called it the standard normal table. That I don't care what mu and sigma you have, I always can come up with a number or an area like the 196 and 1645. But if I don't know sigma, things become more complicated. We'll introduce that next time and simplify it. Okay? So I hope you enjoyed this session. It wasn't so tough on you. I know it's dry, but that's the nature of probability, unfortunately. But when you get to understand it, you will love it, I'm sure. Have a nice day and hope to see you soon.